So laminar flow in tubes. When the flow is laminar inside the tube, then how we can calculate the heat transfer? So basically, we'll calculate the Nusselt number or the heat transfer coefficient H. So ultimate target is we'll calculate the Nusselt number or the heat transfer coefficient H. Here you can see a lot of mathematical expressions. This is the cross-sectional view of the differential volume. This is the element, and it's showing the derivations. Um, you know, we do not need to understand all of these things. Here is the detailed calculation step by step. If you go through the books, then you will see all these calculations. But we do not need to drive this in the exam. But what we need to do is we need to calculate the Nusselt number. So here is the final term. Here is the final term. So T is temperature. So the net rate of energy transferred to this control volume by the mass flow rate is equal to the net rate of heat conduction in the radial directions. Here, R is, you see, it is changing with R. So this is the radial direction. So we do not need to know about it, but just let's quickly say what is happening here. So for constant surface heat flask, we found from the calculations the Nusselt number for laminar flow. This is constant 4.36. What it means? It means for fully developed laminar flow in a circular pipe, the Nusselt number is constant. When it is a constant surface heat flask condition, Nusselt number is not changing. It's constant. So that means it doesn't depend on Reynolds or Reynolds number. I'm repeating again. If a constant surface heat flask condition exists, then for laminar flow inside the pipe, Nusselt number is constant. So this is the first thing. Then, if we have the other condition for constant surface temperature, then the Nusselt number is again 3.66. And you know when we have the pipe flow like this is the fluid going this directions, so we have some the frictions. So we can calculate this frictions factor. For laminar flow, it is always constant. F equal 64 over RE. This is for the circular pipe. Now the question is, if the pipe is non-circular, then how we can calculate the Nusselt number or the friction factor? So the circular pipe means this is the cross section. So we have this is the inlet. We know the diameter, but for non-circular pipe, we don't know the diameter. So then we will calculate the hydraulic diameter. Hydraulic diameter is this. It is the 4 perimeter over the cross-sectional area over perimeter. AC is the cross-sectional area, and this is the perimeter. So what do we need to do? We need to substitute this value to the Nusselt number definition, and then we can get it like this. So the heat transfer coefficient for a non-circular pipe, it will be this. It is the hydraulic diameter, not the normal diameter, but the hydraulic diameter. Here is the chart that will make your life easier. For circular tube, for constant surface, okay, 3.6 is constant heat plus 4.36. If it is rectangle, ellipse, or the triangle, then what you can do, here is the calculations. This is the ratio A and B. So for this ratio, you can see the corresponding surface Nusselt number. This is for the Nusselt number. Yeah, this 2 column is for Nusselt number, and this is for the friction factor. So you can easily calculate it from here. So if you have a rectangle, this length is 4, this is 2. So that means, it is 4 over 2, that means 2. So here is the information. So if it is a constant surface temperature, it is the Nusselt number. For constant heat flask, this is the Nusselt number, and this is the friction factor value. And how you can calculate the entrance region? If it is laminar flow, okay. So the entrance region, we will calculate these expressions for the Nusselt number. Okay. So if you have the length long enough, then you see it will be 3.66. You look here, it is 3.66. So it will depends. When For the fully developed value, it will be 3.6. This term, it will be kind of 0. It will, okay? And when the difference between the surface and the fluid temperature is large, then we'll use these expressions. And here's the last one for isothermal parallel plates. When the Reynolds number is less than 2800, it look this condition. When the Reynolds number is less than 2800, we'll use these expressions to calculate the Nusselt number. Okay, so for this one, you know, this is when this conditions is when the Prandtl number is greater than or equal 5. We'll use these conditions when the Prandtl number is 0.62 less than or equal 5. So here is the conditions. So we'll discuss it more during when we will solve the problems. So that's it, and I believe this is very easy concept, especially for the laminar flow.